In this lesson, we're going to apply the side splitter theorem to parallel lines cut by transversals. And we're going to do kind of an informal proof. The theorem is, if three or more parallel lines are cut by two transversals, then the segments of those transversals are in proportion. So here we have three parallel lines, or we're going to say they're parallel, and they're cut by these transversals. We're going to look at this by drawing an auxiliary line, and we're going to create two similar triangles that share a common side. The auxiliary line I'm going to draw is going to connect the upper left to the bottom right. That doesn't look exactly right. Let me see if I can do this again. You can do this better on your paper, as always, than I can do this on the iPad, but if I just... There we go. So here we have two triangles. We have three parallel lines, and we have a triangle here, and we have a triangle up here. So we have an x and an x prime and a y prime and a y, and then you can see here they share this side. So I'm going to label this segment A and this segment B. And then we can write some ratios here because of these parallel lines. Right here I know that x over y is going to equal to a over b. So let me write that. X over y is equal to a over b. And we can do the same thing with the other pair. I have these two parallel lines, so I know that y prime, or x prime over y prime, is going to be a over b. And then all we need to do is look at this, and we know by the transitive property that if two things are equal to the same thing, they're going to be equal to each other. So I can actually set x over y equal to x prime over y prime. So I don't need that auxiliary line anymore. We don't have to do this intermediate step. Now we know that when parallel lines are cut by two transversals, their sides, their segments, are going to be in proportion. So we're going to demonstrate this concept in a few examples here. Here we have, we're going to assume that lines that appear parallel are going to be in fact parallel. We're going to make that assumption for all these exercises. So here we have a basic one. We have 9 and 3 and 12 and x, and I know we just proved that I don't need the full triangle here, or we don't need to draw that auxiliary line to show that 9 over 3 is going to be equal to 12 over x. 9 over 3 is equal to 12 over x, and then we can solve for that value. 9x by cross multiplying is 36, and in this case x is going to be 4. So it's the same principle as the side splitter theorem. We're just applying it to parallel lines now. So here's our second example. This just happens to have the parallel lines turned, so now they're running vertically instead of horizontal. And here's our two transversals. So again, we know from that theorem that the ratio of this side is going to be equal to the ratio of this side. So I can say x over 4.125 has to be equal to 2 over 5.5. My writing's not very good today. So when I cross multiply, I get 5.5x is equal to 8 1/4. And when you divide, you end up with x is 1.5. Again, just using that concept that parallel lines cut by transversals, their segments are going to be in proportion. So now in this very short lesson, we're going to apply this concept to a trapezoid, and then take a look at the perimeter. So we're just going to make this slightly more complicated. And we'll work through one here, then we'll work through more examples in class. So we have AB is parallel to EF, which is parallel to CD. So I'm going to label those. These are my parallel lines. And so AC and BD are the transversals. The only thing different here is that I'm not extending my line, so I've got a shape, and I've got to remember the relationship between the parallel lines and these transversals. And basically, what that means is BF to FD is going to be the same as AE to EC. We can't say anything else about the parallel lines because that wasn't part of our theorem. So let's label what we have. We have AB is 20, So that's the bottom. I can't use that one in a ratio though. And CD is 8. FD is 12. I can use FD in a ratio. And then I have this. I know that AE to EC is 1 to 3. So I don't really know exactly what it is, but this is kind of the scale factor here. So AE over EC is going to be equivalent to 1 over 3. That does not mean that AE is 1 and EC is 3, but I can take this ratio and apply it to the other side. So I can find BF. And then, from there, we'll take the perimeter and figure out the rest of it. So we'll use this ratio to solve for x and set up our proportion here. X over 12 is going to be, since the x is going with the AE, and the AE is with the 1, that means x over 12 is going to be equivalent to 1/3. So we don't have to actually have the sides, the value of the sides, as long as we have the scale factor to work with, it's all going to be the same. So when I cross multiply, I get 3x is equal to 12. So my x value should be 4. So now this guy is 4. If I can change him, I'll just say he's 4. I'll put him in red here. And now let's see what else we have to do. We have the perimeter. So if we know the perimeter of trapezoid ABCD is 64, we want to find AE and EC. So again, we don't know AE and EC, but we do know is their ratio 1 to 3. So now if I want to solve up there, if I want to say AE is y, then EC is going to be 3 times that. So now I have one variable because we do know what x is, and we can solve using the perimeter. So the perimeter is adding everything all the way around, which means 20, as I go around, plus 4 plus 12 plus 8 plus the 3y and the y. That is all equal to 64. So combining like terms and simplifying, I believe I have 44 if you had the 20 and the 4 and the 12 and the 8, plus 4y is equal to 64. This lets us solve for y, and then we can substitute back in. If y is 5, that means this answer goes up here for AE, and AE is 5, and EC is 3 times that. EC is going to be 15. So that's my final answer. And all that does is use all the ratios and the perimeter concept to kind of have a problem that has a few more steps to it. So we'll practice some more of this stuff in class.